Welcome to Savi YouTube channel, Sai Vidya Institute of Technology. In this lecture video, I am going to discuss sum of two random variables and their expectation parameters. Now, let us consider two random variables which are independent in nature, that is x and y. We know that the random variables x and y are said to be independent or uncorrelated if the covariance between the random variables x and y is 0. So assuming the random variables are independent, then if I define one more random variable w, which is sum of the independent random variable x and y, that is the random variable w equal to x plus y, then the mean of sum of the two random variables x and y can be written as e of x plus e of y. Therefore, mu w equal to mu x plus mu y. Similarly, the variance of the sum of the two random variables x and y can be defined as, in terms of w, the variance of the sum term x plus y is given by, it is an expectation operator operating on w minus mu w whole square, where mu w represents the mean of the random variable w, which is equal to mu x plus mu y, where w is the sum of the two independent random variables x plus y. Substitute the value of w and mu w and simplify the expectation operator, then we are going to get the variance of the sum of the two independent random variables as sigma w square equal to variance of the random variable x plus variance of the random variable y plus 2 times the covariance between the random variables x and y. Since the random variables x and y, they are independent in nature, the covariance between the random variables x, y is 0. Therefore, for sum of two independent random variables x and y, the variance of the sum term is given by, it is a sum of the variances of the random variable x and random variable y, which are independent in nature. Well, we'll define what is a PDF of the sum of the two independent random variables x and y. So we know that w equal to x plus y. Its PDF is given by fw of w equal to integral over minus infinity to plus infinity f x of x into f y of w minus x with respect to x. That is the PDF of the sum of the two independent random variables. It is given by the convolution between the random variable x and the random variable y. So it is a convolution sum. Therefore, if the two random variables x and y are independent, then the PDF of the sum term x plus y is given by the convolution between the PDF of the random variable x and the random variable y. Here star represents the convolution operator. So I can conclude that the PDF of the sum of independent random variables x and y is given by the convolution integral between the PDFs of random variable x and random variable y. Now we'll study how to determine the characteristic function of the sum of the independent random variables x and y. We know that the characteristic function is indicated by w of j omega. Here w represents the random variable, so it is defined as, it is an expectation operator operating on e to the power of j omega w. We know that w equal to x plus y, so simplify using laws of indices, so you will get the expectation operator operating on e power j omega w equal to expectation operator operating on e power j omega x into expectation operator operating on e power j omega y. e power j omega y. By using the definition of pi x of j omega, so e power expectation operator on e power j omega x is nothing but characteristic function of random variable x, and expectation operator on e power j omega y is nothing but it is characteristic function of random variable y. Therefore, the characteristic function for sum of two independent random variables, it is a product of the characteristic function of random variable x and random variable y. This particular concept, it is mainly used in the applications in communication system when the noise is combined with any signal, then the resulting signal is a sum of signal plus noise. Now under such condition, if the signal is independent of the noise, then this particular concept can be applied to simplify the statistical parameters and to extract the signal under the presence of the noise.